Welcome to our practical guide on difference-in-difference, or DiD, estimation using EViews. This method is a cornerstone of modern econometrics for causal inference. The core idea, as quoted, is to understand the counterfactual. What would have happened to the treated group if they had not received the treatment? DiD provides a powerful way to estimate this. Imagine we want to know the effect of a new fertilizer on crop yields. We can't just compare yields before and after, because the weather might have changed. DiD helps us use a control group of farms that didn't get the fertilizer to isolate the fertilizer's true effect from the weather's effect. But before we can estimate this effect, we must first understand the fundamental problem that DiD is designed to solve, the causality problem. This slide introduces the causality problem, which is the core challenge in determining if a policy or intervention truly caused an observed outcome. It highlights two common pitfalls of naive methods. First, we have selection bias, which occurs when comparing a treated group to a control group in a cross-section. The issue is that these groups might have inherent pre-existing differences, meaning any observed differences in outcomes might not be due to the treatment, but simply to these initial disparities. Second, there's time trend bias, relevant in time series analysis when comparing outcomes before and after a policy. Here, outside economic or other trends occurring simultaneously with the policy can confound the results, making it seem like the policy caused a change when it was actually these broader trends. The goal in addressing this causality problem is threefold: to isolate the true impact of the policy, to construct a valid counterfactual, meaning what would have happened to the treated group if they had not received the treatment, and finally, to subtract the control group's trend from the treatment group's trend to identify the policy's specific effect. This slide outlines the necessary conditions and a checklist for when the difference-in-difference, or DiD, method is appropriate. First, you must have panel data, meaning you observe the same entities across multiple time periods. Second, there needs to be a specific policy intervention that occurred at a defined point in time. Third, your data must include both a treatment group, which received the intervention, and a control group, which did not. Finally, the intervention itself should be binary, meaning an entity either received the treatment, coded as 1, or did not, coded as 0. If all these conditions are met, then DiD is a suitable estimation method. On the right, we have a data checklist for additional considerations. Ideally, you should have a balanced panel, meaning all units are observed for all time periods, though unbalanced panels can also be accommodated. A clearly defined treatment date is crucial. You need a clear control group that truly remained untreated, and it's vital that this control group is unaffected by any spillover effects from the treatment, which would contaminate the comparison. This slide breaks down the core difference-in-difference regression model. YIT equals alpha plus beta treat I plus gamma post T plus delta treat I times post T plus epsilon IT. Here, YIT represents the outcome for individual I at time t. The alpha is the intercept. Beta treat I captures initial group differences between the treated and control groups before the intervention. Gamma post t accounts for general time trends that would affect both groups. The crucial term is delta treat I times post t, which is the interaction term. This is our key coefficient and represents the causal effect. It measures the extra change in the treated group's outcome in the post-treatment period relative to the control group, thereby effectively canceling out pre-existing differences and common time trends, isolating the impact of the treatment. This slide visually represents the most critical assumption in difference-in-difference estimation, the parallel trends assumption. It states that, in the absence of the intervention or treatment, the outcome trends for both the treatment group and the control group would have followed the same path over time. As you can see on the graph, before the intervention, both the treatment group and the control group lines move in parallel. This is the crucial pre-intervention period where we verify this assumption. After the intervention, the treatment group line diverges from its original path. The dashed line labeled counterfactual illustrates what would have happened to the treatment group had the intervention not occurred. It would have continued to follow the same trend as the control group. The vertical brace, the treatment effect, quantifies the causal impact of the intervention. It's the difference between the actual outcome for the treatment group and its estimated counterfactual. The critical rule on the right emphasizes that groups do not need to start at the same level. They don't need to be identical, but their trends must be parallel before the intervention. If these trends diverge before the policy is enacted, then any estimated treatment effect would be biased, as we couldn't confidently attribute post-intervention changes solely to the policy. EViews makes running a DiD model incredibly straightforward. First, you need to ensure your data is structured as a panel work file. This is a critical prerequisite. Once your panel work file is set up, you navigate to the main menu. From there, the path is simple. Click on Quick, then Estimate Equation. In the Equation Estimation dialog box that appears, you will change the estimation method to DiD, Difference-in-Difference. A major advantage of the EViews DiD estimator is its default use of two-way fixed effects, or TWFE. Under the Panel Options tab, you'll see that cross-section and period effects are both set to fixed. This TWFE specification automatically controls for any unobserved, time-invariant characteristics of the units, like a state's unique economic structure, and any unobserved, unit-invariant shocks that happen over time, like a nationwide recession. You don't have to manually create dozens of dummy variables. The estimator handles it all. We're going to dive into a classic case study from economics, the 1994 research by David Card and Alan Kruger. Their work directly tackled a fundamental economic question: does raising the minimum wage kill jobs? Conventional economic theory at the time largely predicted that it would lead to job losses. However, Card and Kruger's groundbreaking difference-in-difference analysis challenged this widely held belief. They examined a natural experiment where New Jersey, our treatment group, raised its minimum wage in April 1992, while neighboring Pennsylvania served as the control group, maintaining its lower minimum wage. The dependent variable they studied was employment in fast food restaurants. We'll explore their methodology and aim to replicate their findings to understand this pivotal study better. Data preparation is critical. Here, we need to create a single treatment variable, which we'll call Newman. This variable is not just a dummy for being in New Jersey, nor is it just a dummy for being in the post-1992 period. It is the interaction of the two. The variable Newman equals 1 only if the observation is for New Jersey, the treated unit, and the date is April 1992 or later, the post-treatment period. For all other observations, it is 0. This single variable effectively captures the treat I times post-t term from our equation, which is what the EViews DiD estimator requires. Look at the data. The observation for PA in November 1992 has Newman equals 0 because it's the control group. The observation for NJ in February 1992 has Newman equals 0 because it's before the treatment. Only the observation for NJ in November 1992 gets a 1. With our data correctly prepared, we can now run the model in EViews. In the equation estimation window, we specify our model. The dependent variable is employment, empt tot. We include C for the constant term, or intercept. Crucially, in the treatment variable box, we enter the name of the dummy variable we just created, Newman. Notice that we do not need to manually create the interaction term in the equation specification. EViews understands that Newman is the treatment variable and will use it to calculate the DiD effect automatically. A common mistake is to write empt tot CNJ post NJ times post in the equation box. With the dedicated DiD estimator, you don't need to do this. The specification is much simpler. Empt tot C in the main box and Newman in the treatment variable box. After clicking OK, EViews will run the estimation and present us with the output table, which we'll now learn to interpret. The key result is the coefficient on our treatment variable, Newmin. This coefficient represents the average treatment effect on the treated, or ATT. In this case, the coefficient is 2.33. Since it's positive, it suggests that, relative to Pennsylvania, employment in New Jersey's fast food restaurants actually increased by 2.33 employees per restaurant after the minimum wage hike. This result directly contradicts the simple job-killing hypothesis. However, we must also check for statistical significance. The p-value, found in the prob column, is 0.145. Since this is greater than the conventional threshold of 0.05, we conclude that the result is not statistically significant. We cannot confidently say the effect is different from zero. EViews automatically provides a test for our key assumption, the parallel trends test. The null hypothesis, or H0, for this test is that the pre-treatment trends are indeed parallel. This is a situation where we use reverse logic. Unlike most tests where we want to reject the null hypothesis, here we hope to fail to reject it. A failure to reject H0 provides support for our model's validity. The p-value for the test is 0.3061. Since this value is large, much greater than 0.05, we fail to reject the null hypothesis. This is good news. It means we have statistical evidence that the parallel trends assumption holds, and our DiD model is valid. Statistical tests are powerful, but you should always supplement them with visual diagnostics. A picture can reveal patterns that a single p-value might miss. You should always plot the average outcomes for the treatment and control groups over time. Visually inspect the period before the treatment date. The lines for the two groups should move roughly in parallel. If you see the lines clearly diverging or converging before the intervention, it's a major red flag that the parallel trends assumption is violated, regardless of what the statistical test says. The Goodman-Bacon decomposition is an essential diagnostic for addressing timing variance in difference-in-difference models, especially when treatment dates vary across the panel. This decomposition breaks down the overall DiD estimate into good comparisons, which are between treated and untreated units, and bad comparisons, which occur when early treated units are compared to late treated units. By separating these comparisons, it ensures that your result isn't unduly driven by potentially biased comparisons arising from staggered treatment adoption. You can typically find this diagnostic under View, then DiD Diagnostics, and finally, Goodman-Bacon decomposition. The Callaway-Sant'Anna, or CS, estimator is a modern, robust alternative to the standard two-way fixed effects difference-in-difference model. It is specifically designed to handle staggered treatment adoption and situations where treatment effects might be heterogeneous, meaning they differ for various groups or over time. A key advantage is that it avoids the bad comparisons problem by never using already treated units as controls. Current best practice is to report your main result from the standard DiD, and then show the results from the CS estimator as a robustness check. This helps confirm that your findings hold up under these stricter, more flexible assumptions. The table on the slide presents example Callaway-Sant'Anna group time effects, showing the average treatment effect on the treated for different groups and time periods, along with their standard errors and t-statistics. This method handles heterogeneous treatment effects better than standard two-way fixed effects. This slide provides a quick summary and a syntax cheat sheet for a difference-in-difference estimation. We'll cover the essential workflow steps and highlight key EViews commands. First, let's look at the workflow checklist. You begin by loading your panel data. Next, you define your treatment variable, which is often an interaction of state and post-period dummies. Then, you estimate your DiD model. Finally, and crucially, you check for parallel trends. For efficiency, remember that while the graphical user interface is excellent for learning, using syntax is best for replicating your work. Specifically, the .did command is incredibly useful for fast iteration and refining your models. The command line syntax shown here demonstrates how to estimate a DiD equation named EQ1, with mtot as the dependent variable and newmin as the treatment variable, along with a constant c. The second line shows how to freeze a graph of the DiD trends from the EQ1 output. This slide includes references for the material discussed: EViews 13 User Guide, III, Chapter 56, Card, D, and A, Kruger, 1994, Minimum Wages and Employment, and Goodman-Bacon, A, 2021, Difference